All right, welcome back everybody. In this video, we're going to handle content from section 10.9 of AP Calculus BC, the last lesson of our first half of our unit on convergence tests, etc. And in this video, we are going to talk about how we determine absolute or conditional convergence. Okay, so let's see. We mentioned the idea of absolute convergence and conditional convergence very briefly. What we're going to do is we're going to talk in this lesson about what it means to converge absolutely, what it means to converge conditionally, some strategies that we're going to use to determine whether a series converges absolutely, converges conditionally, or diverges, and then we're going to work through a few examples. So inside our box here, we get started with the notion of absolute or conditional convergence. So suppose we have some series, sum of a sub n, and that it's an infinite series. If the sum of the absolute value of a sub n converges, that means that the original series here is absolutely convergent, or we will say it converges absolutely. Okay? This is why we don't talk about absolute and conditional convergence with non-alternating series, because when we have a non-alternating series, the series is its own absolute value. And so it's impossible for us to have a situation where the absolute value of the series converges, or pardon me, where the series converges but the absolute value doesn't when we've got a non-alternating series, because they're the same thing. This is why when we talk about absolute and conditional convergence, we're talking about it with regards to alternating series. The second little bullet point here, I kind of got ahead of myself. If the sum of a sub n converges, but the sum of the absolute value of a sub n diverges, then the original series here is what we say conditionally convergent, or we'll say that the series converges conditionally. This is, what I was just talking about it being it is impossible for a non-alternating series to converge conditionally, because the series itself and the absolute value of the series are the same series. So it's impossible for one of them to converge and the other to diverge when we're talking about a non-alternating series. And that's why we only talk about absolute and conditional convergence with alternating series. And then, of course, the third possibility, if the original series diverges, that means that the absolute value is also going to the series of the absolute value is also going to diverge. And that means that the original series is divergent. All right. We can really approach this however we want to. We can kind of go piecemeal and say, oh, let's test the absolute value, let's test the original series, and depending on what happens, you might just stumble upon the right approach walking in the door. I generally use the strategy that I'm about to outline. I usually start with step 1 and work towards step 4, but every now and then I start with step 3 if I have a particularly strong hunch about the behavior. But typically this is the path that I go down when I'm trying to decide if a series converges conditionally, converges absolutely, or diverges. First thing I do, because it's super easy, is I use the nth term test to see if the series diverges. Okay? If the limit as n approaches infinity of a sub n equals 0, then the nth term test is inconclusive, but if that nth term approaches anything other than 0, the series diverges. If the test is inconclusive, I proceed to step 2. I test the absolute value of the series and see if that converges by using some test that we know. If the absolute value converges, then that means the original series converges absolutely. If not, then we proceed to step 3. We test to see if the original series converges using some test. Usually in this case we'll use the alternating series test because we're testing the convergence of an alternating series. If it does, then the series converges conditionally. Otherwise, that means that the series diverges. Okay, so that's kind of my strategy for approaching these. I don't follow it to the letter 100% of the time, but the vast majority of the time, that's what I'm doing when I'm trying to decide whether a series converges absolutely, conditionally, or diverges. So let's look at example 1. Does the following series converge absolutely, converge conditionally, or diverge? So the first thing I try is I try the limit as n approaches infinity of a sub n in my original series. Okay, so I'm going to take the limit of this as n approaches infinity, and that limit is equal to 0, so the nth term test was inconclusive. All right. Then I test to see if the series converges absolutely. So I'm going to take the absolute value of this series. So we'll look at the absolute value and see, does it converge absolutely? The absolute value of this series is the sum from 1 to infinity of 1 over n. This diverges because it's a p-series with p equal to 1. So this series does not converge absolutely. Then I go on and I test to see if it converges conditionally. All right, this is an alternating series test where a sub n is equal to 1 over n. Does the limit as n approaches infinity of a sub n equal 0? Yes. Is a sub n greater than or equal to a sub n plus 1? For n greater than or equal to some number, I'm going to say 1. And the answer to that is yes. Okay? So, by alternating series test, sum from 1 to infinity of negative 1 to the n plus 1 times 1 over n converges. Okay, so it did not converge absolutely. It did converge when we tested it for conditional convergence. So our conclusion here is that this series converges conditionally. All right, example 2. Does the following series converge absolutely, converge conditionally, or diverge? So again, I start with the nth term test. And a lot of times the nth term test is going to be inconclusive, but on those rare occasions that it is not, it can save us a lot of work. And it's not a lot of work to do the nth term test to begin with. So we do this because it's a super simple rule. And we find here that it is inconclusive. Okay, then we try to see and test absolute convergence. So we want to test the absolute value of the original series. That's the sum from 1 to infinity of 1 over n cubed. This converges because it is a p-series with p greater than 1. And now I'm done. Once I find that it converges when I'm testing it for absolute convergence, I'm done. We will say, sorry, my hand got ahead of my brain there. We will say that this series converges absolutely. Okay? Absolute convergence is a little bit stronger than conditional convergence. Okay? Knowing that it converges absolutely, we know that the alternating series here converges as well. Whereas when it doesn't converge absolutely, only the alternating series converges, not the absolute value of it. All right, example 3. Does the following series converge absolutely, converge conditionally, or diverge? We start with the nth term test. Limit as n goes to infinity of negative 1 to the n, 2n squared plus 3, 3n squared minus 1. Well, this bounces back and forth between 2/3 and negative 2/3. Either way, this does not equal 0. And therefore, this series diverges by the nth term test. All right, let's keep chugging here. Example 4, does the following series converge absolutely, converge conditionally, or diverge? We try the nth term test. And so we're going to take the limit as n goes to infinity of -1 to the n times n over n cubed plus 2. And that is going to approach 0, so the nth term test is inconclusive. Then we try and see absolutely. So we're going to test the sum from 1 to infinity of n over n cubed plus 2. All right, I'm going to compare this. I'm going to do limit comparison. Compare to the sum from 1 to infinity of 1 over n squared. Now the limit as n goes to infinity of n over n cubed plus 2 times the reciprocal of this, limit as n goes to infinity of all this, is going to be equal to 1. So, by limit comparison test, these two series share convergence. Therefore, since sum from 1 to infinity of 1 over n squared converges because it is a p-series with p greater than or equal or greater than 1, sum from 1 to infinity of n over n cubed plus 2 converges. So, sum from 1 to infinity of -1 to the n times n over n cubed plus 2 converges absolutely, since the absolute value of it converges. All right, that seems like a good place for us to stop with this first video. We're going to come back and do the last 2 examples of this lesson, and in our next video. All right, so we'll see you then. Have a great rest of your day, everybody, and enjoy yourself. Have a good time. Bye-bye.